Okay, let's dive in and just see where this goes. No planning for this video. Let's get the pen out. Pen's working. Okay, so your coordinates will be X and Y. Robot always starts at 0, facing in this direction for the time being. And then we give a desired coordinate point. We're going to call this 0.5, 0.5. The new driving method should create a behavior where we curve, we don't do any point turns, and then we drive forward. So every waypoint has two sections. The curve of a constant radius, maybe in the code it's a lowercase r, and then a distance of straight driving in wherein both segments, curving and driving, we're measuring the change in theta, the change in the heading of the robot, where theta is not the heading, but theta describes the movement. Basically, it's the heading of SCUTTLE in his frame, and we're checking dx. And for a distance of 500 millimeters and 500 millimeters, maybe we'll be driving and performing 100 or 200 segments. That's just how fast we're going and how fast we're sampling. So this will be something like 1 millimeter to 5 millimeters. I'm not quite sure, but that's the basic scale. Now let's look at the curve section and the criteria for everything. Our very first point, I'll start it in orange, and our very first motion will have some curving and some advancement. So we'll keep orange. This is zoomed in a lot, okay? This is going to be, let's just say that's 4 millimeters arc length. And we have to do two things after this. Update heading and update the X and Y global positions, so the translation of the robot. Because these are so small, and this might be the maximum often this might only be 0.5 millimeter, I'm not sure, but because this distance is so small, we're not going to consider the fact that it's an arc. We're going to consider that it's a straight line for the keeping the math low intensity. It's already fairly intense because of the other kinematics being done, but here's what's happening. This is the heading, and the initial heading, let me use yellow, and I'm going to call this, we'll call it theta I, initial, and then I'm going to make a red one, okay, and this is theta final. And so if you compare those two, you get, we'll just use orange again. Maybe it's a little bit stronger than that. Okay, so d theta is right there. In this case, theta I was 0. Maybe we don't need to use that. But in order to calculate this, this x movement from here to here, blue equals the translation. We'll come back to it, but to calculate our translation we have to choose how we want to calculate it without using an arc, because the arc's math is more intensive. So what we're going to do is I'll use a sharp purple. We want to use this angle and pretend that instead of starting out at the yellow area and ending up at the red area, that actually the whole time we just drove in the purple direction. And so this would be in the code, this is called, I don't think we even name the variable, we just start using it. We put it in the short part of the code, it's used to create a rotation matrix. So I'm sorry, but this is theta for the function, and that equals d theta over 2. And in the rotation matrix, this needs to be added to d theta over 2 must be added to the previous heading, which is actually called self.heading. I don't know how to denote this, but the self.heading has not been updated. When we perform this calculation. So this is the theta function. In code it's just called theta, but it's local to one function and it's never called again, so you won't know that that theta is special unless you just read the code. But it's okay because it's not used anywhere else. And then that's put into a rotation matrix. That's a capital R. Which is something like cosine theta minus sine theta. Okay, da 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 da. This is a standard 2D rotation matrix. I don't want to get my signs wrong, so it's just an array of cosines and sines. And then we perform the rotation matrix where we take the displacement we believe took place was this. So on your robot, you have the x displacement. So when you're driving and we're calculating using kinematics the x advancement, there is never any y translation. It's always in the x. So you have a vector that looks like this dx and 0. And that is the, that's called, what do we call it in the code? Draw vector. Oh, it's called the local vector. Okay, because that's the displacement in the local coordinate frame. And then we multiply r times the local vector, which looks like shoot. this kind of thing, and that gets us the global vector. Okay, so this one describes the translation for each increment. We come up here, that means every time we drive a tiny amount, such as 1 millimeter or 4 millimeters, the global vector that's added to the existing position, this between these two blue lines, is that value, the global vector. That's a product of these, and of course it's a 1 by 2 shape like this. Now you should have in mind an idea of the scale. So somewhere in the XY coordinate system you have your actual position of the robot, and that means this purple vector is actually quite large, and when we add this global vector to the global position, it's basically saying, okay, now I perform this small deviation, and then you have a new global position. Okay, I didn't need to zoom out that much. So in the end, every single translation is treated as a straight line, and the angle that we're using for that is an average between the angle of our heading before and after the movement. And then finally, updating the heading is extremely easy because we just take basically the heading equals the heading plus the displacement, angular displacement, yeah. Which comes directly from the kinematics. Which we should know gets fed by wheels. We have phi dot left and phi dot right. Excuse me, there's no dots here for this set of variables. It's just the phi increment. And you could say then, when we deal with increments, you could just say that's a delta. Right? That's all for this video.